Hello viewers, I am Dr. G. Littlefla, faculty from the Department of Physics, Stella College, Vijayawada. Happy to welcome you all for a talk on binding energy of nuclei. So, what keeps these nucleons, protons and neutrons inside the nucleus and make the atom stable? So here we come across this term binding energy. It is the energy required to split the nucleus into its constituents. We can also say that binding energy is the energy required to make the nucleus. So two ways we can say energy required to split the nucleus into its constituent particles, protons and neutrons, or the energy required to bind the protons and neutrons inside the nucleus is called binding energy. Binding energy gives the information on the force among the nucleons, stability of the nucleus against disintegration, and how much energy is released or required in nuclear decays or reactions. So there are some atoms which are naturally radioactive in nature. That means the nucleus undergo disintegration and release enormous amount of energy. So all this can be understood if we know what is binding energy. Next, another important term is mass defect. Now, scientists have found out the mass of the nuclei of particular element, and we know the mass of each proton or neutron that makes the nucleus of any element. Now suppose in a particular atom, if we add the mass of the protons and the mass of the neutrons, some number is coming. But if you find the mass of the same nucleus, we find that the mass of the nucleus is always lesser than the mass of the nucleons. So this difference is called mass defect. The difference between the mass of the nucleus m and mass of nucleons is called as mass defect. There is a defect. So protons and neutrons only make the nucleus. So we expect that the mass of the nucleons together must be equal to mass of the nucleus. But when we make the measurement, we find that mass of the nucleus is always lesser than the mass of the nucleons. Nucleons are nothing but the protons and the neutrons. So this can be represented by a formula, mass defect equal to delta m. A small difference will be coming. That is equal to z into mp plus a minus z into mn minus m. So here z represents the atomic number of protons, into mp is mass of each proton. How many protons are there? That into mass of proton gives you total mass of the protons. Next, we know A is the mass number and Z is the atomic number. So from mass number represents number of protons plus number of neutrons. Now we know the number of protons. So from the mass number A, if we subtract the number of protons, we get that number of neutrons. So A minus Z represents number of neutrons. So Mn represents mass of each neutron. So if you multiply the number of neutrons with the mass of the neutron, we get the total mass of the neutrons. And we add total mass of protons plus total mass of neutrons, or we can say total mass of the nucleons is always greater than the mass of the nucleus. So here we have said that the difference between the mass of the nucleus and the mass of the nucleons. So as mass of the nucleons is always greater, this minus this gives us the mass defect. Thus mass defect is the difference between mass of the nucleons and mass of the nucleus. So this mass delta m is converted into an amount of energy by Einstein's relation. We know E equal to m into c squared. M is the mass and c is the velocity of light. So this delta E, very small difference. So we represent it as delta E is equal to mass defect into c squared. That means how much amount of mass is disappearing, that will be converted into energy using Einstein's relation. This energy is called binding energy of the nucleus. That means why this difference? Why mass of the nucleus is always less than the mass of the nucleons? So certain amount of energy goes in binding them together inside the nucleus. So the energy, binding energy, the same amount of energy is required to break the nucleus into its constituent particles. So if you want to make the nucleus or break the nucleus, you need this much amount of energy, which is given by delta E equal to delta M into c squared. Next, another term comes here. This is called packing fraction. It is represented by the letter F. Packing fraction F is equal to mass defect by mass number. How much mass defect? The ratio of mass defect and mass number gives you packing fraction. So mass defect we represent it by delta M. Mass number we represent it by A. So it is a ratio of mass defect to mass number. Now binding energy is equal to mass defect into c squared. Mass defect, in the earlier slide we saw the formula ZMP plus A minus Z into Mn minus M into. So this is the mass defect into c squared. Now M is mass of the nucleus, c is the velocity of light, Mn is the mass of neutron, Mp is the mass of proton. Z is atomic number, which is equal to number of protons in the nucleus. A minus Z represents number of neutrons. So mass number A is the sum of protons and neutrons, that is called mass number. Now binding energy per nucleon. Binding energy per nucleon means you have to divide it by the mass number. The binding energy per nucleon of a nucleus is the binding energy divided by the total number of nucleons. So here we can represent the binding energy per nucleon as a function of mass number in a graph. So binding energy per nucleon, the unit is in million electron volt is taken along the y-axis and the mass number is taken along the x-axis. So x-axis we have taken 20, 40, 60 like that, and binding energy 2, 4, 6, 8, 10 like that. So here what happens? So as the mass number increases, binding energy also increases. Mass number increases means number of nucleons increases. So many elements. So we have from hydrogen to so many other elements are there. As mass number increases, binding energy slowly increasing. Except these three atoms like helium atom, carbon atom and oxygen atom, the curve is a smooth curve. So here some exception is taking place. So what happens when the mass number is increasing from 1 onwards, binding energy is increasing. When it comes to helium, binding energy becomes very higher. Then for lithium and the other elements it is decreasing. Again for carbon it is increasing sharply and then decreasing. And when for oxygen, it is 16. Mass number is 16. As mass number increases, you can see for oxygen atom also, it is sharply increasing, then decreases, then onwards smoothly it is increasing. So here there is some exception. Except these three elements, generally binding energy per nucleon increases gradually as the mass number is increasing. Okay, the graph we name it as binding energy per nucleon as a function of A. Okay, so this is the graph. Now in the graph we come across certain points. So let us see the first point. It is observed from the graph the binding energy per nucleon except these three atoms rises first sharply and reaches a maximum value of 8.8 million electron volts around A equal to 50 and corresponds to the most stable nuclei. So many elements are there in the periodic table. If we refer, more than 108 elements are there. Okay, so among them the element which has mass number 50 has a maximum binding energy. So binding energy is very high, means its stability is very high. If you want to break the nucleus, it's not that easy because binding energy is very, very high. So 8, 9, 10. So binding energy becomes maximum when A becomes 50. And afterwards binding energy is slowly decreasing at around 140. When mass number becomes 140, the binding energy becomes 8.4 million electron volts. And then as the mass number increases, it decreases, and the minimum value of binding energy is around 7.6 million electron volts. Okay, so here we said that A equal to 50 has a maximum binding energy. So we have, in our daily life, we use iron in many ways. For example, constructing building and all. Why we choose iron? So many elements are there in the periodic table. Why we choose iron is, iron is represented by the letter Fe, and it has mass number 56, which is closer, around 50, that has maximum binding energy per nucleon. So our iron element is lying closer to this, and we find that iron is one of the most stable element on earth. That's why while constructing building and all, we go for iron material. Okay, it is the most stable nuclei that exists. Then the curve falls slowly at around A equal to 140. It reaches the value of 8.4 million electron volts, and then binding energy decreases at around 210. It becomes 7.6 million electron volts. So if you check the binding energy of the nucleus per nucleon for the elements in the periodic table, we find that it is increasing, reaching the maximum value, and the minimum value will be 7.6 million electron volts. And this curve never meets 0. Means if you want to make an element, the nucleus, then binding energy is required. Binding energy cannot be 0. That's why the curve doesn't start from 0. So we have hydrogen. For hydrogen maybe here. For helium, it's going up like this. And the curve goes, and the minimum binding energy is around 7.6 million electron volts. Binding energy can never be 0. If it is 0, there is no such element also existing. Okay. Next one, some inferences we can get from this graph. Inferences are very important, so we get some idea. So excluding the lighter nuclei where the binding energy is this, here and all, most of the elements, if you see, so if you skip this part, most of the elements, so here maximum is 8.8, here at around 140, 8.4, at around 210 it is 7.6 million electron volts. If we take the average of this, we can say that if you leave the lighter elements, generally average binding energy per nucleon is around 8 million electron volts. 8.8, 8.4, 7.6, average if you take around 8 million electron volts. So if we keep aside the lighter nuclei, generally binding energy per nucleon is around 8 million electron volts. Then nuclei with very low or very high mass numbers have lesser binding energy. So if you see here, binding energy is only this much, here this much only. So elements with a low mass number, or if you take elements with a very high mass numbers, again binding energy has decreased from 8. So binding energy of the nuclei that have low or very high mass numbers will have lesser binding energy per nucleon and are less stable. So among the elements marked in the periodic table, if you see the lower row, the elements at the lower side, that means they're having lesser mass number, or higher side, they will be not that much stable. So it is easier to separate the nucleus into its constituent nucleons. For example, this side, if you see uranium, it's a radioactive element. Its mass number is around 92, and so all that, see 92 here, so my binding energy is becoming less. So binding energy is less, and mass number will be 235. So maybe here. So whatever it may be, binding energy is least. So binding energy is least means, okay, for uranium, atomic number is 92, mass number is 235 or 238, two isotopes it has. So in terms of mass number, if you see, as the mass number is very high, the binding energy is around 7.6 million electron volts only. So it is easier to break the nucleus. That's why uranium by itself, it's disintegrating into its daughter nucleus, and the radioactive series goes and stop at lead. Okay. Then another new inference is that nuclei with low mass numbers may undergo nuclear fusion. So we have fusion and fission. So this is the most stable element. So if you take up elements lower than A equal to 50, you can make the fusion reaction to take place. Fusion means lighter nuclei joining together form a new nuclei. So while making or breaking, huge amount of energy is released from the nucleus. That is what called nuclear energy. This energy can be converted into electrical energy and supplied for our electrical needs. So even the elements with the low mass number can be made to undergo fusion reaction, and by this lighter nuclei can combine and form a new nucleus. Due to this combination, enormous amount of energy can be released, which can be put into application. Same way, the elements with the higher mass number also, the binding energy per nucleon is less, so easily it can disintegrate. So above A equal to 50, those elements can undergo fission. Fission means the nucleus, just because its binding energy is less, it gets split up and form a new nuclei with which has more stability. Okay, so that final whether fusion or fission, the nucleus split to, see here in fission, the nucleus split to give two daughter nuclei with the release of neutrons. The daughter nuclei will possess greater binding energy per nucleon. So daughter nuclei will have more stability than the actual nuclei itself. So you can see, you get an idea which are the elements can undergo fusion, which are the elements that undergo fission. So fission means breaking the nucleus, and the big nucleus break into two daughter nuclei, releasing lot of neutrons and energy also. That energy can be in an atomic nuclear reactor and all. Mostly fission reaction only taking place. From that we get from that nuclear energy we get that nuclear energy can be converted into electrical energy. So here I have presented a small problem to get more idea about binding energy per nucleon. So here the binding energy of lithium, we want to calculate the binding energy of lithium. This atom has mass number 7 and atomic number 3. That means atomic number represents the number of protons, which is equal to number of electrons. Mass number represents number of protons and neutrons together. So from A, if you subtract Z, you will be getting number of neutrons. Okay, so the lithium nucleus has 3 protons and 4 neutrons. So you are given mass of the proton this much number, mass of neutron is also given, mass of the lithium nucleus is also given. So we have the formula. Okay, so first you have to find out mass of the protons. So number of protons 3 into mass of the proton, it gives. Same way you have to calculate what is the total mass of 4 neutrons you are getting, and mass of the nucleus is given here, where mass of the lithium nucleus is given. So mass of protons plus mass of neutrons together we are getting. So this is the mass of the nucleons, total nucleons. Now we know mass defect is mass of the nucleons minus mass of the lithium nucleus. Mass of the lithium nucleus is given here. So from this, when you subtract, you are getting mass defect in atomic mass unit. That mass defect can be converted into binding energy of the lithium nucleus. This is nothing but mass defect into 931, because one atomic mass unit is equal to 1.66 into 10 power minus 27 kg. This can be converted into million electron volts, so that becomes 931.48. So what you do, mass defect, straight away if you multiply by 931, you will be getting what is the binding energy of the lithium nucleus. So here it happens, it is 37.7 million electron volts. That much energy is required to break or make the lithium nucleus. Okay, if you want to break the lithium nucleus, you need to supply energy little more than this so that it can be easily broken. So if you want to calculate what is the binding energy per nucleon, what you have to do, 37.7 by the mass number. So if you want to add one nucleon to the nucleus, you need this much energy to be supplied. So another example I have given, hydrogen has 3 isotopes. The first isotope, it has one proton or one proton and one electron here. It is the lighter isotopes of hydrogen, contain one proton and one electron, called hydrogen. It has a mass this much value. Then you have deuterium, the next isotope of hydrogen. Okay, this is the most abundant element. It has 3 isotopes. Isotopes means number of protons will remain the same. So here the first isotope is protium, number of proton is 1. Here deuterium, here also number of proton 1, here 1 neutron is added here. So that way this is different from this isotope. Here only 1 electron and 1 proton. There is no neutron in the hydrogen nucleus. Whereas in the deuterium, you have 1 neutron. Okay. This is a heavy hydrogen, we call it. And then it consists of 1 proton and 1 neutron. So you have twice the mass of the nucleus of ordinary hydrogen. So if you see here, mass of the atom is almost equal to mass of the nucleus. So here mass of proton 1, whereas here mass of proton and mass of neutron to be added here. So this mass of this deuterium nucleus is almost twice that of protium. We have one more isotope for hydrogen. Here you can see number of proton will be here 1, but 2 neutrons it has. 2 neutrons. Here no neutron, here 1 neutron, here 2 neutron. That way hydrogen has 3 isotopes. So you can say that tritium has 3 times the mass of the protium, or I can say tritium, or 3 times of this hydrogen nuclei, we can say. So hydrogen also we represent 1, 1, 1. This gives actually mass of electron and number of electron and number of proton. And here no neutron, here 1 neutron, here 3 neutrons. So once again I give another problem, calculate the binding energy of deuteron. So deuteron means nothing but deuterium. So you must know the this formula, like H with representing 1 electron means here 1 proton. Electron and proton number should be the same, so that neutron doesn't have any charge. So atom as such is neutral. So number of proton must be equal to number of electron, because electron has negative charge and proton has positive charge. Atom as such, its charge will be 0. So this is possible when the electron number is equal to proton number. So now the question is, calculate the binding energy of deuteron. So binding energy formula we must know number of protons, number of neutrons, and mass of the proton and mass of the neutron, and mass of that deuterium nucleus also must be given. So here they have given mass of proton, mass of the neutron, and you can find out what is the total mass of the nucleons. actual mass of the deuteron is given here, so you can find out what is mass defect, multiply it by 931, then you will be getting binding energy. So next, another new term I am introducing here is magic numbers. Magic numbers refer to those nuclei. So we are speaking more of nucleus. I am not telling about atom. The nucleus is inside the atom. About the nucleus we are speaking. So whenever we speak about nucleus, there comes one special concept, that magic numbers. These numbers are numbers that represents some nuclei will have their nuclear number which is equal to magic number. So they will be, what is that? Let us say in nuclear physics, a magic number is a number of nucleons in a nuclei where the shells are completely filled. The first shell, second shell, third shell. Those cells, first shell can hold only 2 electrons. Second shell can hold 8 electrons, like that. If they are completely filled, then the nucleus achieve a state of low energy and high stability. So whether that nuclei is stable or not, we can make it out by knowing the magic numbers. If magic numbers are there, you can simply say that those nuclei will be highly stable because that they possess less energy. Low energy but high stability. So what are the numbers? So there are 7 most widely recognized magic numbers. Still research is going on and scientists are finding some other magic numbers also. So far what is completely approved by the scientific community is nuclei that are having nucleons number, either proton number or neutron number. If it is equal to 2, 8, 20, 28, 50, 82 and 126. So those elements whose nuclei has either proton number or neutron number or the nuclear number, any one of these numbers, then those nuclei will be having higher stability. Higher stability. So if magic number of Z represents the number of proton and N represents the number of neutron, either proton or neutron number is any one among these 7 numbers, they will have large binding energies per nucleon. So those nuclei will be highly stable. Some examples are given here. You can see helium. Here proton number is 2 and neutron number is 2. So both the proton number and neutron number 2, 2. So it is one of the magic number. Here you see this is electron number. So mass number is electron number is equal to proton number. So out of 16, 8 will be protons, 8 will be neutrons. Once again you can see second magic number, maybe proton number or neutron number or both is equal to a magic number. Those elements will be highly stable. See, for example, oxygen, which gives us life, has higher stability. Suppose if this nature it doesn't have, oxygen will disappear, we all will suffer without oxygen for our breathing. So here you can see 8 protons and 8 neutrons, both the nucleons have magic number. Here you can see calcium. In calcium also proton number is 20, neutron number is 20. So both nucleons have magic number. 20 is another magic number. And then lead. Lead is having 82 protons and 126 neutrons. So 126 is a magic number. So these elements can be called as doubly magic nuclei. Why doubly magic nuclei? Both the protons and neutrons have number is equal to one of the magic number. So if both the proton and neutron have their number as magic number, then we can call it as doubly magic nuclei, and these elements will be very, very highly stable. Okay. For example, radioactive series, it may start with uranium, thorium, plutonium, like that. It comes, finally ends with lead. Lead is the most stable element. Same way, so elements with nuclei having doubly magic numbers will be highly stable because binding energy is very high. So some more experimental evidences for the existence of magic number. Is it true that we have magic number? So some experimental evidences are coming here our way. The first one is binding energy of the magic number nuclei is much larger than the neighboring nuclei. So larger energy is required to separate a single nucleon from such a nuclei. So magic number, those nuclei that has a magic number, the nuclear number is magic number, will have much larger binding energy, so it is not easily breakable. Then number of suppose if proton number and neutron number is a magic number, such elements will have more isotopes than the number of stable nuclei with the neighboring values of Z and N. Suppose if you take an element, its neighboring nuclei. So this particular nuclei will have a nuclear number is magic number. The next, the previous one, if you consider, they don't have. So here one example I give. We choose tin. Tin has atomic number 50. Atomic number is nothing but proton number 50. 50 is one of the magic number. Okay. This tin has 10 stable isotopes. That's what we say here. If the nuclear number is equal to one of the magic number, such nuclei will have more isotopes. Now proton number is 50. So this tin has 10 stable isotopes. In the previous slide I showed how hydrogen had 3 isotopes. Hydrogen has 3 isotopes. Here tin has 10 stable isotopes. Now the neighboring elements are indium and antimony. Indium has proton number as 49 and antimony has proton number as 51. So closer to the magic number 50, but they have only 2. So its magic number is, that proton number is not equal to magic number. Not equal to magic number, though it is very close by, but has only 2 stable isotopes. So this statement clearly explains if the nuclei has proton number or neutron number corresponding to the magic number, then they will have more isotopes. So tin has proton number equal to 50. 50 is one of the magic number. It has more 10 stable isotopes. This example would have clarified this point. Now, those nuclei whose nuclear numbers equal to the magic number, they have greater relative abundances. That means they are more available in nature. So here we have taken strontium. Okay, here neutron number is 50. In barium, neutron number is 82. And cesium, neutron number is 82. So 82, here 50. So these elements like strontium, barium and cesium, whose proton or neutron number is one of the magic number, they will be available, relatively available more in nature. They have relative abundances of strontium has 82.56%, 71.66 and 88.48 respectively. And 3 naturally occurring radioactive series end at lead. I said no, radioactive series like uranium, thorium, polonium, they all will end with lead, because lead atomic number is 82 and neutron number is 126. Both are magic numbers. So lead is doubly magic number, so highly stable. So all the radioactive elements, once they get converted into lead, the radioactivity stops because it is highly stable. Then if N is a magic number, then cross section for neutron absorption is much lower than for other nucleides. So N, if neutron number is a magic number, maybe any one of 2, 8, 26, 50, 86 and 126, their cross section for neutron absorption, those nuclei whose neutron number is a magic number, it cannot absorb neutron because the cross section for neutron absorption is much lower than for other nucleides. Okay, and nuclei with the value of n just one more than the magic number, neutron number is more than just by 1 the magic number, spontaneously emit a neutron. So you can see here oxygen is 8 protons and how much, 9 neutrons, so just one above. So these elements naturally emit a neutron. Nuclei with magic numbers of neutrons or protons have their first excited states at higher energies than in cases of neighboring nuclei. So if the nuclear number is a magic number, they have their first excited states will be at higher energy. And electric quadrupole moment of magic number nuclei, all those nuclei, those have nucleons number equal to the magic number, electric quadrupole moment becomes 0. If electric quadrupole moment becoming 0, it tells that the shape of such a nucleus will be spherical in nature. So if electric quadrupole moment for the nucleus is 0, which nuclei can have 0 quadrupole moment? Those nucleons whose number is equal to a magic number. So if the nuclei has a magic number, then they will have spherical structure. Energy of alpha or beta particles emitted by a magic numbered radioactive nuclei is larger than from other nuclei. So those nuclei that undergo radioactivity, if they emit alpha particles or beta particles, those alpha particles or beta particles will carry higher energy than the alpha particles and beta particles emitted from the other nuclei. There are more stable isotopes if atomic number is a magic number, and more stable isotones if n is a magic number. So we come across new terms. Isotopes means all the isotopes will have same proton number. Isotones means same neutron number. So if the nuclei has proton number a magic number or neutron number, proton number a magic number, they will have more isotopes. If neutron number is a magic number, they will have more isotones. The neutron or proton separation energies. What is separation energy? The energy required to remove a neutron or proton from the nuclei of the element become maximum if neutron or a proton number is equal to a magic number. Already this point we said, if proton number or neutron number is equal to a magic number, that element will have higher stability. So you need more energy to remove a proton or a neutron from such nuclei. I hope you would have understood the various concepts of binding energy, packing fraction, and which type of nuclei will be having more stability, which type of elements can undergo fusion reaction, fission reaction, and then magic number. So just by knowing the magic number, you can say these elements will be more stable. And if you want alpha particle for some medical use or something, higher energy if you want, from which elements you can choose. Though the radioactive elements all can emit, you go for the elements whose nuclear number is a magic number. They can give out alpha or beta particles with higher energy. So accordingly, those particles can be put into applications. Thank you one and all for listening to me. We will meet in another video with another interesting topic. Thank you.